Today's topic is classifying matter. So grab a paper, pencil, and periodic table, and we'll get started. Before we can classify matter, we need to know its definition. And matter is anything that has mass and volume, or another way to say volume is it takes up space. So let's write down some examples and some non-examples. And look around the room that you're in. There are many things that have mass and take up space. Some examples could be a desk or a person or a pencil that you're writing with, or iron, an element. Some non-examples would be things that don't have mass, don't take up space, would be energy, could be your thoughts, your emotions. And one that stumps some students is air, because it's something that we can't see, but the air around us actually has mass to it. It's made up of molecules of oxygen and carbon dioxide and hydrogen gas and water vapor. That's all matter. Doesn't have a lot of mass, but it has some mass. And we know it takes up space. If you blow up a balloon, you see that the balloon then occupies a certain space. So we're going to make sure that we put air in the example side so that we don't make that mistake and think that air is not matter, because it is. Let's also take a quick moment to differentiate between mass and weight. So mass is the amount of matter that's in a substance, and weight is that mass times the force of gravity. And we want to make the distinction between those two words because weight will vary depending on your location and the gravity at that location, but mass will remain the same as long as the amount of matter in the sample hasn't changed. We're going to create a flow chart to help show us the classification of matter. And I recommend that you hold your paper landscape. It just gives you a little bit more room to write. So starting at the top, we're going to label it classification of matter. And we're going to put matter right in the middle at the top. And we're going to divide it into two sections, pure substance on the left, mixture on the right. Now, a pure substance is going to be uniform matter with a constant composition. So there's only one type of particle. And this means that no matter where you find the substance, it's always going to have the exact same composition and the same proportions. It doesn't ever vary, whether you find it in the United States or you find it at the bottom of the ocean or you find it on a different planet, it's always going to have the same composition. And a mixture is something that contains more than one substance. We're going to break the pure substances down into two parts, and we're going to start with elements. Now, the elements we can find on the periodic table, and elements are going to consist of just one kind of atom. So we know it has to be pure or the same all the way through, or has a uniform composition because there's only one type of atom there. We're not going to be able to chemically break these atoms down into smaller pieces because they're already down at the atomic level. Some examples, you might have hydrogen, oxygen, chlorine, iron. Notice how some elements have one letter in their symbol and some elements have two, but every symbol starts with a capital letter, and if there's a second letter, that second letter has to be lowercase. Second category under pure substances is going to be compounds. And in a compound, you're going to have two or more different elements bonded together with a chemical bond. So you don't have just one type of atom, you have to have at least two different types of atoms within a compound. Now, because these atoms have been chemically bonded together, you could break that bond, so this can be chemically broken down into a simpler substance or back into the original elements. Some examples of these could be CO2, H2O, or even iron bromide. Notice how when we write the different elements with their symbols, there's no space between the carbon and the oxygen and carbon dioxide. They are right next to each other, and that tells us that they are bonded together. Now, it's important to remember that when the elements come together to make a compound, they have created a brand new substance. They're no longer their individual elements, and these compounds can have properties that are different from the elements that form them. And here's a great example of that. If we were to take sodium, Na, it's in the first column of the periodic table. It is extremely reactive. So reactive that if you put it in water, it's going to explode. It's very dangerous. If you had pure chlorine gas, That's another element off the periodic table. It's going to be a greenish gas. It is highly toxic. If you breathe that in, you could easily die. So we have two very dangerous things, but you put them together and they form a bond with each other and they turn into NaCl. And that is something that we use all the time in our kitchen and we put into more food than we should because it tastes good. So once it bonds together, it takes on new properties that neither of the elements had when they were individual elements. So let's make sure we include in our flow chart the chemical equation for the reaction we were just talking about. We have 2Na reacts with Cl2, yields 2NaCl. And over on the reactant side, where the Na and the Cl are not combined, we're going to label that side as hazardous. And on the NaCl side, where they are combined, we're going to label that as harmless. Well, it's not completely harmless. You don't want to have too much sodium chloride in your diet, but compared to what we started with, it's going to be considered harmless. We're going to move over to the other side of our flow chart with mixtures. Remember, a mixture has to have more than one substance in the container. If it's a heterogeneous mixture, it is not the same all the way through. And when you look at it, you're actually going to see different parts inside the container or inside the sample. Some examples could be a chaw salad. When you look at that, you obviously see many different parts. The olives, the cucumbers, tomatoes, onions, lettuce, obviously not the same all the way through. A chocolate chip cookie. You see the chocolate parts and the cookie parts. Here we have an example of oil and water. It's not evenly mixed all the way through. We can see the oil suspended within the water. Obviously, two different substances mixed together. And another example could be the sample of granite, because there's different colors in there. There's some grays, some blacks, even some pinkish hues within that rock. So these are all examples of heterogeneous mixtures because they're not the same all the way through. And when we look at it, we can see different parts. So let's include a couple of those in our flow chart before we move on. So the last column in our flow chart is also going to be underneath the mixture side, and that's going to be a homogeneous mixture, which is going to be the same all the way through. It's uniform from top to bottom. And they're also called solutions. Any solution is going to be considered a homogeneous mixture. Some examples of homogeneous mixtures could be tea. Gatorade is an excellent example. It's water and food coloring and flavoring and electrolytes and sugars. And it's uniform all the way through. The first sip of Gatorade tastes just like the last sip because it is uniform. This is unusual. A French horn when we're talking about homogeneous mixtures? Well, at first it does seem unusual, but brass, which the brass instrument is made of, is a homogeneous mixture. It's a mixture of two different elements, copper and zinc. Now, in order to mix metals together, you have to melt them down, and while they're molten, you can mix them together and then let them cool, and they'll solidify, and the copper and zinc are uniformly mixed all the way through this instrument. So let's write down under homogeneous mixtures that anything dissolved in water is going to be a solution or a homogeneous mixture. Now, that means that when you put it in water and you stir it up, the solid disappears. It doesn't turn cloudy. It doesn't settle to the bottom. You won't see what you put in the water anymore. It's going to be evenly distributed throughout the water. That would be a homogeneous mixture. We also want to add in alloys where you have a solid solution. We typically think of solutions as being liquid, but we saw that alloys are also homogeneous mixtures. And they're going to be mixtures of metals. And we should write down a few of those. We had brass, stainless steel, sterling silver. You could add 14 karat gold if you'd like, pewter. There are many different ones that we can put down. We don't need to know all of them, but we do want to have a handful of examples. So now you should have a completed flow chart that looks kind of like this one here. And it's going to be helpful to you as we're getting started with our practice. You can refer to the flow chart to determine whether something is An element, a compound, a homogeneous mixture, a heterogeneous mixture, whether it's a pure substance or not a pure substance. Notice how pure substances are both elements and compounds. Hang on to this flowchart, keep it in your notebook, use it frequently. And thank you so much for joining me today. I will see you soon.